Welcome to Hackon Online. In the chat, you have the opportunity to ask questions, so if you have any, please put them there. It is a pleasure for the Hackon team to present Gerhard. Welcome.
Thanks. Yeah, it's nice to be here today. I'm happy to have you here with my talk, Adventures with Zyxel Routers, Hacking Routers like it's 1996. First, short introduction about myself and my colleague, which unfortunately got sick and so couldn't attend. So I will run this whole presentation on my own. But anyways, Steffen Roberts, the guy which I did the most work with, and me, Gerhard Hechenberger, we're security consultants at SecConsult, and we're mostly doing embedded systems and IoT penetration tests. We're working as researchers also in the Vienna hardware laboratory of SecConsult, and have pretty much the same focus topics about, as I said, IoT and embedded systems tests, including also hardware. We also do a lot of OT infrastructure and do a lot of hardware research on the side. Special thanks also goes out to Thomas Weber and Stefan Fieböck, which were supporting with this research and this whole project. The vendor Zyxel, because in the end, everything, or a lot of that stuff got fixed at least. And the SecConsult Vulnerability Lab, which is our central position of vendor vulnerability disclosure supports with all that. And yeah, so we'll start. A little bit of a background beforehand. I will talk about CPE devices this today. So what are CPE devices? It's named customer premises equipment. That means it's hardware which is provided to you by an internet service provider and connects you to the ISP network. So like this router you have sitting at your home desk, which gives you internet at home. And the thing for this CPE devices is they're usually normally kind of normal routers. It's just a little bit of specific branding or a little bit of modification, sometimes more modification. So you may just replace one color or the whole web interface. And often you also have additional hardening measures because the router now belongs to your ISP and sits in your home. It's not like it's your router. And another thing, because they want to disable features, they want to do that because to get less tickets for support. So if you don't have any option to configure your router, okay, here I am again. I guess the Chrome tab just crashed.
Yes, we lost you there for a minute. It seems like Big Marker has some problems keeping the feed from both you and the audience or attendees, so let's try again.
Yes, so next try. Just pick the correct screen. Yes. Here we go. Yeah, hopefully second try works better. Yeah, I was stopping at ISP equipment and definitely want to disable features because then they get less support requests. Because if you can't configure something, you can't misconfigure something. And yeah, for that, they want to strip down the functionality. Also, they want you to have less attack vectors on their infrastructure because, yeah, it's the ISP's infrastructure and they want to protect that with different, yeah, measures. And there's also this kind of threat model as I said, what do they want to protect from? First thing, yeah, of course, this thing connects you to the internet. So yeah, attackers on the internet and attackers on the physical network, which means if you have yeah, infected client in your network, that's kind of your internal attacker now, but also attackers with physical access. And you might think, yeah, what about physical access? Who gets access to my flat to access the router? It may be you. So because it's, yeah, for the ISP, you are maybe the physical attacker. And that's what, because they want to protect different stuff on these devices. And one thing is they want to protect the integrity from you and also attackers on the internet, because there's botnets or you could have surveillance on people, and then you can connect back to the ISP infrastructure. For that, there are credentials, web credentials or ISP credentials on the router. And the ISP does not want you to get these, because then you could do kind of bad stuff with that or attack their infrastructure. So they want to protect them, the credentials from you. And yeah, I said it's an adventure. So we go on here as an adventure, and we start on the upper left corner. Yeah, that's us. And I will guide you through the whole process of yeah, discovery of things, and then go on until the disclosure. Yeah, like how does these projects start? It's Monday morning, you had your first coffee and unpack the devices you just got shipped. You plug it in and then connect to the web interface and do a little bit of analytics. You connect to the web interface, you see the open ports. Yeah, you start the assessment. Usually you get credentials. Here on these devices, usually you get an admin user. It's named admin, doesn't have full permissions. And then you explore the functionality on these devices. Yeah, and it was just some minutes and we discovered this ping window in the router. And these are always interesting. They keep on giving. And you could put an IP address in there. And next thing is, yeah, for sure, they would sanitize the input, right? Yeah, that's the first step in our adventure and the first vulnerability. And yeah, just put in the shell and profit, because then we had root access on the device. They don't do any input sanitization on the IP here. So you can just add an additional command and wait for your shell. And we're root, so full access to everything. And it was just, yeah, first half an hour of the day. Learning here, I mean, we have some learnings in here, because you should do that better if you're a vendor of that, or if you're building software or hardware. So learning here is you should sanitize input on the server side. We'll see why this is important later. Yeah, that was a quick first start. We go on to the tear down. We explored the functionality, and then we do an in-depth assessment. And so we tear the device open, look at the hardware, see what you can get there. And on the hardware, we have the main SOC. It's a Broadcom SOC. We had a RAM IC in there, and we had some SPI flash and a suspicious header, which turned out to be a UART header, serial header. We connected to. Two interesting things here is the header and also the memory, because this will also give us more information. We connected to the UART header. It's quite simple with a UART translator, and got a shell on there. It's kind of a limited size shell where you can log in with your credentials. You could also use like on the web interface. And we went on for dumping the memory. Second interesting part here. This is kind of easy to dump. It's an SPI flash. There are way more complicated flash types to dump out there. It was supported by FlashROM. We dumped it using our own extractor hardware. And you see the entropy diagram on the right side. That's the thing you typically do after having dumping a memory, having some files there. You can do an entropy diagram, because if you have a stable entropy of 1, it's usually something encrypted. And here we see an alternating pattern, which means it's close to 1. So it means it's most likely compressed, but not encrypted. And we see it, we use binwalk to extract that. We see it as a UB volume in there. So great, we can extract the files from the file system. And this is where it goes on from our teardown to the analysis part. We use Git for that. And reverse engineering started. Because if you have the firmware now, you can have a look into a lot of binaries and do kind of more white box-like testing. And there we had some interesting thing in there. We had this export log endpoint. We didn't know from the exploring features on the web interface. So it was kind of new or not used on the web interface itself. And yeah, we saw this and saw you could put in some parameters. And it turns out after another analysis of that, that it's a file disclosure, a built-in feature file disclosure. Because at the export log endpoint, you could just add, after a question mark, a file, and you get this file back, which is awesome, because now you can just, from a standard device, get the etc password in shadow, so you can get the user hashes on there. And there's a specialty on these routers, because they have a central configuration. This is a JSON file where you have all the interesting stuff in there, so you can also roll back configurations. And you could also access this too. And we see it down there. We have different parts in this JSON, and also the interesting juicy parts, like the SIP credentials mentioned before. Internet service provider wants to protect them, and also the users of the system itself. And you see it. It's not in clear text, like the passwords are encrypted, something like encrypt, and it was some value after that. And then you have also the passwords in there. So the username, the root password encrypted, and the shadow value, and an SMB password. And this is an NTLM hash. And as you might know, it's far easier to crack NTLM hashes as the SHA-512 crypt hashes of Linux. So this was already some start, but of course, we're interested in the encrypted parts here. For the file disclosure itself, it's again sanitization of input. Log export was meant for exporting log files. It was not meant to put an absolute path in there and to retrieve any file. And you should always also check authentication, because why are we allowed to use this endpoint after all? Yeah, it goes on. They store sensitive data in an encrypted format and have their own format for that. And we found the hard-coded key in there, which brings us to our next vulnerability we had. We analyzed this encrypted data. There's a prefix, the encrypt prefix. We had base 64 encoded data after that. We found out through reverse engineering that it's ASCBC encryption with a key derivation algorithm. And this key derivation algorithm uses a static password and a static salt in there. This was already known to be used by Zyxel. There not this exact algorithm, but there are a lot of, or you can find it on the internet, there are some algorithms already reverse engineered. They tend to have kind of a new iteration in some routers and have different flavors of this encrypted data. But initially, in the end, it's kind of all the same. You have some hard-coded static password in there. And then, of course, this goes on. You have to implement the key derivation. We did that in C, then the decryption in Python. And now we had a program, a small program, where we could decrypt these encrypted values. You see it here, for example, it's password 1234, and because we're lazy doing that, we didn't strip the padding you see after that. Yeah, and I have said it before, here it is again, 3 slides before the local file disclosure. We now can decrypt all these files. So if we have unauthenticated access on the LAN side of this router, we can now extract this configuration and just decrypt these parts. Or we can also dump the memory, of course. But yeah, it's easier to just use the web endpoint. So we now had a decrypted root default password and also the SIP credentials, which, yeah, ISPs are not looking forward to that. Learning here as, again, to limit sensitive data. So why is the SMB password stored here? Have some SMB functionality in there, but it lowers your security. You should use proper encryption, and proper encryption is always hard on embedded devices because that usually means you need some secure element, which cannot just be read. And you should also use encryption which is tied to the device itself. So no shared static key. Yeah, it goes on. Next thing we found was access control in general. So we had some features. We had of the log export endpoint. It was not visible in the user interface. And with unprotected API endpoints, which we found, some API endpoints which were used for administrative tasks, usually with higher permissions, or at least we think it was targeted at that. Like changing configs for SSH and FTP, also reading various data of users and permissions we should not have access to. And yeah, there was this endpoint, the management service. And there you had the configuration of the services, and we queried that, and it was SSH is open on the trust domain. And yeah, we found out we could send data to that. So we sent data and set the mode to LAN and trusted domain, which means now it's open on the LAN interface. And yeah, so we queried it again. It was accepted. And so now we had SSH access on our router. What a pity, we just got the same size shell again. So kind of limited shell where we could log in with our standard admin user we got at the start. Yeah. Learning here is it's not enough to remove the features in the user interface. Somebody will discover them. And again, you should check the authorization and do that, of course, on the server side, because otherwise you can just circumvent that. And the story continues. So week continues, story continues with a lot of other minor parts, like you could enable FTP, and then you had FTP following symbolic links, which mean you set a link for the root system of the device and can then extract the files on there. Also, you had a very interesting implementation of CSRF. You had an endpoint where you could request a new CSRF token, and the randomness was, yeah, to say it, questionable. Was generated on the basis on some time base. And we also had some cross-site scripting just in the printer service there. Yeah, it was pretty bad already, and then it got worse. We had to dig for the really interesting parts, and this is buffer overflows, where also the title of this talks come from. And we started with the web server because it seemed interesting. The web server used on this device was interesting because it's kind of an own creation. We found out later that it was kind of based on a UPnP server, which was published on GitHub by a user named CyberGarage, and it was modified by Zyxel. It is written in C, so you potentially have all the memory corruption problems. And Zyxel patched some really interesting parts and some core logic in there. And interesting part, which also we found out later, Dan, was that all the issues we found there, we found in the Zyxel modified part and not in the initial implementation. So this interesting thing here was that they used to do the parsing by custom logic, by modified logic. And yeah, poor man's buffer overflow. Just throw A's at the device until something crashes. And it was like, my colleague was asking, oh yeah, then just go have some lunch. And I was just try some last thing. Then we put in a lot of A's just in the URL bar and the device crashed. Why do we know? Because we had full access now on the device. As I said, we had access over UART and we had SSH access. So we could see that in the debugger then also. The device crashed just by standard URL parsing. This was already pretty interesting in there. But I didn't end there because we found a second buffer overflow, and you might not see the difference just now, but have a look at the question mark at the end. Before we had no question mark, so it was like an overlong URL, which triggered a buffer overflow. And here it is the question mark, because if you have a question mark there, they were copying some strings, and they did use the safe string n copy, where you have put in the length of your buffer, so you don't get this problem of buffer overflows. Problem is they didn't really understand what they were doing, apparently, because they didn't put the destination the destination buffer length in there. They put the source string length in there. So it's kind of user controlled length in there. And yeah, that ended up another buffer overflow. And the next part, buffer overflow number 3, you may know this code snippet from before. It's this export log endpoint with a second look on that. And after a question mark, data, the path, gets copied to a buffer. And this buffer is fixed with 256 bytes. So yeah, it was kind of bad. Many buffer overflows, and we decided to exploit one of these. Buffer overflow 3 seemed nice to do that, but not so fast. We had some countermeasures set. There was an NX bit, and ASLR was enabled, but yeah, it was not as proof as it looked, because some weaknesses remained, and it was convenient that they had a watchdog, which was restarting the web server. You will see soon why. Yeah, we have a 32-bit system. ASLR is very limited on these. And after trial and error, we found out it's just about 260 different load addresses. So this will work for brute force, we thought. And we also had no canaries for that. And so we went on for building a ROP chain using return to zero protection. It's kind of return to libc for ARM systems, and to execute a system command. And it was not as straightforward as we had in mind when we were doing that. Sometimes we got a deadlock by jumping just to the wrong commands, because ASLR. When using different gadgets, we improved that, because then we're not ending up in a dead loop. We're just crashing the web server, and you've heard before, the web server is restarting itself after just 5 seconds. So this was kind of convenient for automation. Yeah, so also this was working, And then we had some performance improvements by calculating some buffer addresses via the stack pointer. And also now the exploit in the end only depended on the libc address space. And yeah, we used that. It was implemented in Python here then. And yeah, we got a reverse shell, quite stable via this buffer overflow now. Yeah, that was a lot of different vulnerabilities. Now the other part starts. It's the disclosure process. We reached out to Zyxel to have this fixed. It was, when we were doing that, it was about 2020. So 2021, at the beginning of 2021, we were finished with all that and had the write-up. And we were contacting Zyxel with that. And they confirmed that pretty quick. It's not too bad. And then they were, saying they will have to look for affected devices. And some parts happened in between, but in the end, it took them about a year to find all vulnerable devices. You will soon see why. And then we had a coordinated disclosure together with Zyxel in various steps. So first was out the exploit code. Exploit code was published later on. The last patches were then published at the end of 2020. It was except the 20 devices which were end of life then, so they didn't get patches for that. But at least somebody was accessible there and somebody cared of our vulns. The other part, which we're not really happy about, is Zyxel is their own CNA. CNA is a certificate numbering authority, which means they're allowed to give out CVEs. And all the CNAs have their own area. And if Zyxel has their own CNA, no other CNA is allowed to request CVEs for these area which this CNA covers. So we couldn't just request a CVE somewhere. We had to go the way through Zyxel because they would have to publish or to request CVEs for their own vulns. And they didn't do that. So we were quite sad. And it was quite interesting that some months later, they assigned CVEs. They didn't inform us. We just saw with preparing some information, we saw they did publish CVEs, at least for 3 parts of that. Maybe also because other users were not really happy about how they were handling the CVE process. And CVEs are important because you cannot track vulns if they have not a number assigned. It's just they kind of vanish on the internet because there are so many of them. But in the end, we got CVEs. And sad number of affected devices. It was about over 60 devices which were affected. We listed them in the advisory. That's also why it took them so long to find all the devices. Apparently, they used different code bases and they really had to track them down. That's the disclosure, but we thought it's now really a nice exploitation thing we did here. So why just not go on and implement that for other users as a Metasploit module? And we did that. So it was a large number of affected devices, and we had some really nice primitives. Also based on our Metasploit module, some other user then implemented an even improved module exploit using also other known vulns on these devices. And and kind of beginning of 2023, when we did that, we thought before publishing like a Metasploit module, let's have a look again how many devices are affected or how bad this really is. Because before that, it was like all the stuff we discovered is exploitable over the LAN side, not the WAN side, which means it's not exploitable over the internet. You have to have some leverage over the internal network. But then at this time, we discovered some vendor, some ISP had misconfigured their devices. And yeah, the Metasploit module itself, we have a kind of demo here. It's a video demo, so safe, no praying to the demo gods. I hope you can read that on the screen sharing. It's standard Metasploit module implementation. You first set some arguments after choosing the right module. The options are quite straightforward for you guys, which know Metasploit. This is nothing new. You put in the different IP addresses and then go on. Can check. So Metasploit module has a quick check in there. The target is vulnerable, and then we can start the exploit. We do the brute force approach. We're trying and trying and trying, and eventually we'll succeed with that. And yeah, we have an open multiprocessor session in here. And we go on, start a shell here to see. And yeah, we're root on the device. Pretty convenient now. As I said, Metasploit module and the aftermath, or like during the building of the Metasploit module, we discovered that some ISP had misconfigured apparently their routers and were exposing these web interfaces to the internet. This is, of course, bad. So we contacted them. We never got any recognition, just went into the void. But we saw on Shodan that the devices, the vulnerable devices, were going down. The number of the devices were going down. So at least it had some effect and kind of worked. Would be nice from them to have said some, oh, thanks, we'll change that or something like that. But yeah, at least they did something. And yeah, that was the full story, the full adventure. We went from initial start up down to the tear down and vulnerability analysis with Ghidra over various other parts and various overflows to the disclosure, and then on to the Metasploit part. The conclusion here, we published the advisory. You had it linked also in the description. We did the coordinated disclosure with Zyxel, which took a long time, but in the end worked out quite well. We had 8 vulnerabilities in this advisory, and we had over 60 products which were affected. This advisory was published in 2022, the initial version on the SecConsult Vulnerability Lab, and the Metasploit module was merged and published on Metasploit at the beginning of 2023. Yeah, so what did we learn from that? We're doing that, or we want to present you that because you should learn something from that. Maybe you've seen some attack things you will use for your next time. But also, if you're not in security, if you build IoT devices, you should think about some stuff like having a secure design from the beginning on. So like sensitive data should be encrypted and should be encrypted in a good way, like with hardware or like device bound. Also use appropriate protection measures for that. For the like security implementation, for a secure implementation of input sanitization and executing commands, this is important, like do sanitization, do string length checking, don't just copy, and don't copy with user provided length. You should have quality assurance, because you have to see that the devices also meet your requirements, not just to set them in some paper. And this can be done with quality assurance for you internally, or with external tests like hardware and firmware and pen tests. And as a vendor, you should have a vulnerability reporting process. It went quite okay with Zyxel. We had better, but we also had far worse the vulnerability reporting process. If sometimes it just starts with, who do I contact? Then you write some random email address. Nobody writes you back, and nobody relies the emails. And it's really, really hard sometimes. And you should assign CV numbers, because it makes tracking a lot better for people doing the research and people who want to protect from that. If you buy and use IoT devices, you should have other security requirements. You should know what should this device fulfill. And if you're an ISP, for example, here, you maybe should check the devices before you buy and ship them to your customers. Also here, important, hardware and firmware, because also here we have seen that hardware hacking is kind of essential for a lot of pen tests, because if it wouldn't have been able to read out the software from the memory, it would make some things way harder if it's not as broken as here, because if you have a kind of command injection in the first half an hour, of course, it's not that important anymore. But there are at least better things out there. If there would have been no command injection, we wouldn't have found the buffer overflows, maybe without having access and debugging access to the device itself. That's it, basically. I've seen we had some questions in the chat. Thank you for being here for the talk. And I guess we can go on with some more minutes for answering some questions.
Yes, thank you, Gerhard. First of all, you get a thumbs up from Bjørge. He really enjoyed your adventure map.
Thanks.
And the next question is from Kim Bjørn. He's asking if there are any, as a responsible ISP customer, what should we do to improve protection of our network and internet access?
As a responsible ISP customer.
So he's working for an ISP, so what should they do to make our routers more secure?
The thing is, that's really hard. You can do the research approach, which is not always that fun if it's your router which you use at home, because you may break it and it's not your router. So you're not even allowed to really attack it because it's the router of your ISP. As an end user, you're often on your own. You really have to trust your ISP that they are interested in that, and at least it starts to get better. More and more ISPs start to test the devices before they ship them, and we will get the Cyber Resilience Act from the European Union. This also may be a thing where a lot of companies have a look into that, because then one who sells devices in Europe is responsible to have them kind of secure. We'll see how that works out in practice. But yeah, it's a bad point as an end user. That's the same with a lot of IoT devices, sadly.
I guess as a customer, we should just assume that the routers we get from the ISPs are vulnerable, because they are probably never updated. So to have a security device behind that router is probably advisable.
that is a thing you can do. If you fear from the devices, have your own net behind that, if your router supports that. Because more and more routers you get from the ISP doesn't support this bridge mode anymore, and you get a lot of problems with double net translation. So it starts to be more and more not feasible for that. Yeah. At least for the routers from internet service providers, they start to get updated quite often now for a lot of them, and they get updated remotely. So because also the ISP wants to have their infrastructure secured. It's getting better, but it takes time.
The next question is from Björge. He is wondering what router brands seem to take security more serious, in your opinion?
That's hard. That's again a hard question, also because not if it's the same brand, it doesn't mean that the router is manufactured from the same team or even in the same country. So quality usually varies. Some rule of thumb is if you have cheap routers, they usually don't have money for security. If you have expensive routers, they may have money for security, or they just make more profit on that. It's hard, but yeah, the cheaper, the worse usually that gets.
During your disclosing of different vulnerabilities, do you find that some of the brands have better responsible disclosure policies and respond better back to you?
Yes, we do a lot of responsible disclosure. If you're interested, we have a lot of also advisories up on our website, and we have hugely different experiences. Some really have a straightforward process, like you're going there and you're cared for, and for others, some weeks later, you will get a letter from a lawyer, will sue you for that.
That's a nice touch when you do something security related.
Yes. Yes, that's a nice touch. And that's also why it's always good to have a company backing you, because if you're on your own, you may be like this poor guy in Germany where they raided his home. It was a web developer who found a hard-coded password. And yeah, he's on court now. It's pretty bad if that ends
Have
like
you
that.
ever experienced you or anyone in your team to get a bounty after you found a vulnerability and disclosed it following the set of rules that the vendor have?
It's not a usual thing, but yes, we got smaller bounties. We don't usually do that for the bounties though, but it's always nice if you get something. Yeah.
Next question here is from Levente, asking what was the Shodan search query you used to enumerate the vulnerable devices?
If you're interested to research on that, I'm sure you will find out how you can fingerprint that. But it was decision to not include that because, of course, you find vulnerable devices on the internet with that. So maybe just not expose that too publicly to too many people not knowing what they do, maybe. Yeah.
At least until your routers are secured. Anders has a commentary saying that the problem is not at only the ISPs, since the routers are delivered already faulty, and probably also in some cases they have a custom-made firmware for that ISP. So that makes it probably even more buggy and faulty and full of vulnerabilities.
Yes. That's not only a thing for ISPs. We see that a lot of companies come to us because they want to check the devices they buy. So they're kind of the end users and they're interested. If I have this video conference system, am I vulnerable if I use that in my meeting room? But it shouldn't be like that. It should be like the seller of the system, the people who built these should have to look into security. But everybody is promising you security nowadays. And the more security they promise you, the worse the quality usually gets. So a lot of big companies just said, we have to do a little bit of risk assessment. So let's check all the stuff we get. Yeah, the bad way, I guess, but maybe also, again, the Cyber Resilience Act is improving that a little bit, because this really targets the vendors and the sellers here in Europe. ISPs depends on, some are better, some are worse maybe, but yeah, they're sometimes in the same position as we as end users with vulnerable devices.
Secure by design when we get it will be nice, though.
Yes. And
I do know that a few brands have functionality to automatically update the routers. So if I give one to like my mother, she doesn't have to worry about getting it updated. But that is probably not something that every brand has, is it?
Yes, also newer router models, also because the ISPs want that. They want to update your routers because, yeah, at your grandma's home, your grandma never really does a manual router update. So the ISP wants to secure your device because it's, yeah, the gateway to their infrastructure. Newer models usually have that, the auto update. Then it depends if you're happy with that, because some company is updating a device which is in your local network, which, yeah, it may make you uneasy. Depends how much trust you have.
Perfect. Thank you, Gerhard. I think that concludes this session. So, there's another question at the end. Will new European NIS requirements for third-party security make ISPs legally liable for following up security fixes patching?
That's a quick one because I cannot really answer that. Sorry. I know I have a rough overview about NIS requirements, but it's not going to this depth that I could answer that.
It would be great if it did, though. That's at least
sure.
something we can say.
Great.
Okay, perfect. Thank you, Gerhard, and thank you for watching.
Thank you for having me here.